Hello everyone, my name is Moises Felipe Silva, and I am here today to introduce you to our work, whose title is A Full-Field 3D Experimental Model Analysis from Dynamic Point Clouds Measured using a Time-of-Flight imager. This work is a result of cooperation across multiple institutions and researchers in the US and abroad. Before going into the details of our video-based technique, we need to first define the differences between conventional video-based techniques for dynamic analysis and other imaging solutions in the same field. So usually, video-based techniques for SHM are based on a frame-by-frame target tracking, which usually makes use of artificial high-contrast targets. And then some sort of frame-based template matching is used to track the position of this target and then to compute local displacements, which later can be further used for system identification techniques. Recently, a new set of techniques emerged, attempting to perform full-field high-resolution model estimation over video measurements of vibrating structures. This type of technique makes use of each pixel as a displacement sensor, which significantly increases signal-to-noise ratios. After using phase-based optical flow to compute displacement time series from each pixel, dimensionality reduction is carried out on the basis of principal component analysis. Then, blind source separation is used to directly estimate modal coordinates and mode shapes with resolution equal to the number of pixels in the video. Inspired by that full-field video dynamics technique, here, in this work, we envision the transition of frames to dynamic point clouds. Thus, in the end, our goal is to be able to apply an adapted version of the work proposed by Yang and Mascarenhas over the point cloud data collected for vibrating structures. For this, we propose a simple approach to compute local displacements from point clouds, making the use of the early model identification technique suitable. But first, we need to briefly introduce the category of time-of-flight sensors. Time-of-flight sensors are imagers capable to image scenes and objects by illuminating their surfaces with laser light and measuring the time of reflection of these laser sources, and thus giving birth to the 3D point clouds. Their essential use is to measure depth fields. However, most of these data that comes out from lidar-based sensors have a particular problem until quite recently. The problem is that these point clouds are in most cases static. This feature makes most lidar-type sensors not suitable for direct use for structural dynamics applications. With the advent of the recently commercially available XXXIX, dynamic point clouds at low but enough sampling rates became practical for the development of structural dynamics algorithms. The research questions that arise from these new sensors are mainly the ways to actually leverage dynamic point clouds into model analysis, the level of gains we can obtain, and how to deal with the changing number of points across multiple point clouds measurements. Attempting to answer these questions, a laboratory setup was built using a stainless steel plate excited by a model hammer, with a Kinect measuring the encoding dynamics. An array of laser sensors and an oscilloscope were also used for verification purposes. When comparing the usual RGB recording carried out by the same Kinect and its raw dynamic point clouds, the real differences between frames and clouds start to become clear. In this case, dynamic point clouds share only a single similarity with the equivalent frames, which is the frame rate, or sampling rate. In other words, instead of collecting regular 30 frames per second as in the RGB video, we are getting here 30 point clouds per second, from which we can separate out only the points of interest, in this case the ones corresponding to the vibrating plate. Then, our approach to obtain measurements of the local displacements is to create a mesh of virtual sensors that follows the motion of the vibrating plate. Note that this step is needed to maintain the same number of points across time. This is because the number of points in the dynamic point clouds is changing due to a series of reasons, including noise and imperfections on the structural surface, making vary the number of reflected light beams, and then dynamically changing the number of points in the cloud. Following this approach, in theory, the number of virtual sensors could be arbitrarily increased, making feasible extremely high-resolution full-field model identification with the use of dynamic point clouds. It is important to highlight that the computation of the local deformations is performed using a simple polynomial model, chosen due to its simplicity and low computational cost, a mandatory requirement when processing the volume of data created by the dynamic point clouds. With the local displacement at hand, dimensionality reduction on the basis of principal component analysis is carried out, from which we can verify that the principal components are still a mixture of different modes. Only after applying the complex pursuit-based blind source separation, the individual modes are truly decoupled. A final note at this is that the complexity pursuit was here used due to its known ability to disentangle closely spaced modes. And as the main output of the blind source separation, modal coordinates and static mode shapes with spatial resolution equal to the number of virtual sensors previously defined can be directly obtained. From the proposed technique, the first and second bending modes, along with the first torsional mode, were estimated, with special attention to the torsional mode that could not be directly obtained using regular digital cameras that can only get in plane motion. And of course, the motion of the individual modes can be reconstructed, allowing the visualization of the dynamics of each vibration mode. For comparison, from the displacement laser data, the modal frequencies of the three estimated modes could be verified using the peak-to-peak method, with the indication that the frequency values are in good agreement. Only a 0.4 Hz difference regarding the second bending mode stands out and could be tied to the insufficient 3 Hz sampling rate provided by the imager he used. To summarize, the proposed technique works by decomposing 3D vibration modes from dynamic point cloud data by initially computing local displacements using a polynomial model. Later, it performs dimensionality reduction using principal component analysis and mode estimation via blind source separation, from which modal coordinates and mode shapes can be directly derived. The actual spatial resolution to achieve is tied to the number of virtual sensors created during the computation of local displacements, allowing to simulate the placement of hundreds of thousands sensors currently infeasible with physically attached sensors. To finalize, further envisioned applications involve the prevention of wildfires with the aid of UAVs. With the advent of dynamic point clouds, we can imagine that type of technique he proposed to work along not only with point clouds but other types of event-based imagery to verify the vibration characteristics of vegetation and to correlate with biomass information, providing additional field data to be used in atmospheric and wildfire models. That's it for today. In the name of all co-authors, I hope to have given you a new set of ideas that could help improve your own work. Thanks for watching.